This presentation is about multi-scale screening of adsorbents for post-combustion carbon capture by vacuum swing adsorption processes. In case of post-combustion carbon capture, the main challenge is to achieve 95% purity and 90% recovery from a stream that contains 15% CO2 or less and a large amount of nitrogen. The current benchmark adsorbent is zeolite 13X, and over the last decade, we have seen that new classes of materials like MOFs, COFs, and ZIF are being studied in the context of post-combustion carbon capture. In most of these studies, the focus is to obtain adsorption isotherms either by experiments or simulations and rank different adsorbents based on simple metrics like CO2 capacity at a constant pressure and temperature or CO2 N2 selectivity. The question in terms of the process is A, how do we select the right material, and B, can we rely on the simple metrics like CO2 capacity and selectivity. And in recent publications from the groups of Professors Arvind and Farooq, it was shown that detailed process optimization is a more reliable way to rank materials than simple metrics, and nitrogen adsorption plays a very important role in determining the performance of the process. In this work, we want to study the performance of 4 different materials: zeolite 13X, CPO27 nickel, HCUS1, and silica light in a 4-step and a 6-step VSA process. The aim is to perform detailed process optimization to get specific energy versus productivity Pareto plots and rank these materials based on the Pareto fronts. And for the optimization, we have taken 2 sets of data. One set of data comes from experiments, the other set comes from molecular simulations. This slide here shows the CO2 and N2 adsorption isotherms obtained from experiments. We have also indicated the CO2 and N2 capacities at post-combustion flue gas conditions. And based on this, we can clearly see that the material with both the CO2 and N2 capacity, highest CO2 and N2 capacity, is CPO27 nickel MOF. In this slide, we have shown the adsorption isotherms predicted by molecular simulation from a recent work. These isotherms take into account the presence of binder in an actual pellet, and we can clearly see that the material with the highest CO2 capacity is zeolite 13X, while HCUS1 adsorbent has the highest nitrogen capacity. So to summarize, we see that the CO2 and N2 adsorption capacities are underestimated in most of the materials by molecular simulations, with the exception of zeolite 13X for CO2 and HCUS1 for nitrogen. And we also see that the shape of the isotherm is different for CO2 in zeolite 13X and CPO27. These differences come from the use of generic force fields to estimate the adsorption isotherms. The question now here is, if we use these 2 sets of data, how much of a difference are we going to get in the process performance predictions? And as I said earlier, we have used a 4-step and a 6-step VSA process. The 4-step VSA process contains the following steps: adsorption at high pressure, where preferential adsorption of CO2 takes place when the feed is introduced at high pressure and nitrogen is collected as a right product. Co-current evacuation to an intermediate pressure to remove the nitrogen in the column. Countercurrent evacuation step to a lower vacuum to recover the CO2 product, and light product pressurization step. The 6-step cycle is the 4-step cycle with 2 additional steps. One is the light reflex step, where the column is purged to recover the remaining CO2, and the product of the light reflex step is sent to the rinse step to enhance the CO2 concentration in the bed. To simulate these cycles, we have used a one-dimensional non-isothermal, non-isobaric model. The equations are solved in MATLAB. We have considered a stream containing 15% CO2 and 85% nitrogen. And the aim of the process study is to arrive at minimum specific energy and maximum productivity conditions subject to 95% purity and 90% recovery targets. The optimization was carried out using genetic algorithm. 4,200 simulations were performed for each material in the 2 cycles. The bounds for the decision variables used in these 2 cycles are shown here in this table. The lower bound for the countercurrent evacuation step in the 4-step cycle is 0.01 bar, whereas for the 6-step cycle is 0.1 bar. And the lower bound in the 4-step cycle is necessary because the 4-step cycle needs at least 0.03 bar to achieve the desired recovery. Once we perform the 4,200 simulations, we plot the specific energy versus productivity Pareto. The specific energies here is on an electric basis, and it accounts for the compression and the vacuum energy consumptions. The open symbols in this Pareto front are for molecular simulation isotherms, and closed symbols are for experimental isotherms. The first thing that we can see is that we don't have any points for the CPO27 nickel experimental data, and that is because we did not achieve the desired purity recovery targets. And based on the 2 sets of data, we also see that the ranking is also different. In case of the molecular simulation isotherm data, the best performing adsorbent is zeolite 13X. CPO27 nickel, whereas in terms of experiments, it's zeolite 13X. The other thing that I want to show here is that for AIChE 1, if we use the molecular simulation isotherms, we were not able to achieve the desired 95-90, but rather we achieved 94% purity and 89% recovery. And the other thing is that the productivity values are higher for the isotherms with the higher CO2 capacities. To explain the differences in performance, we plot the specific energy versus the 2 evacuation pressures. And what we can see here is that if your isotherm has a lower nitrogen absorption capacity, the optimizer shows a higher co-current evacuation pressure. And we also see differences in the levels of vacuum with respect to the experimental and molecular simulation isotherms, and that is more prominent in case of 13X. And as you can see that the shape of the isotherms predicted by the molecular simulation is less steep than the experimental isotherms, and this made the optimizer to choose slightly higher countercurrent evacuation pressures. And you can see that 0.01 bar is the lower bound. And these are not realistic in an industrial scale VSA systems. So we move on to the 6-step VSA cycle. And here, more or less, the ranking is the same. The isotherms with the lowest capacity had the lowest productivity. CPO27 nickel, again, based on the experimental isotherms, was not able to achieve 95% purity and 90% recovery. With respect to AIChE 1, in terms of the molecular simulation isotherms, here we were able to achieve 95% purity and 90% recovery. And this suggests that the 6-step cycle is a better cycle than the 4-step cycle with LPP. What was surprising to us was that when we took the experimental isotherm data for AIChE, the performance was worse than silica light. If you recollect from the 4-step cycle, silica light was the worst performing adsorbent. And here this difference is because of the fact that the optimizer chose a shorter adsorption time, which meant that less CO2 is processed per cycle, and that is why we have a lower productivity and a higher specific energy for H-cosmol. If we plot the specific energy versus the co-current and the counter-current evacuation pressures, we can clearly see that for CPO27 nickel, the co-current evacuation pressures were in the range of 0.35 to 0.45 bars, whereas for other adsorbents, it was between 0.2 and 0.3 bars, and that can be attributed to the low nitrogen adsorption in CPO27 nickel. We also see that the counter current evacuation step pressure is between 0.1 and 0.2, and that is much more realistic and achievable in case of large industrial scale systems. We now take a look at the CPO27 nickel purity and recovery values based on the experimental data. And what we see here for the 4-step cycle is that the best purity and recovery were like 90% and 80%. So that was kind of the best performance in terms of purity and recovery. In case of the 6-step cycle, we were able to achieve 90% purity and 90% recovery. This is still not 95-90, but at least it reiterates the fact that each material needs to be mapped to its adsorption cycle, and probably the 6-step VSA cycle is a better performing cycle than the 4-step cycle. A potential solution could be to operate the 6-step VSA cycle at a slightly higher temperature, like 40 degrees. But again, whether the performance would be better than other materials or other adsorbents can only be found out if you do a detailed process optimization. So to conclude, what we have seen here is that when we did the detailed process optimization, we saw that the isotherms with the highest CO2 capacity resulted in higher productivity, but it is not true for CPO27 nickel because it had the highest nitrogen adsorption capacity. So equally important is the nitrogen adsorption. We did process optimization with the 2 sets of data, and what we noticed was the differences in the ranking as well as the absolute values of the specific energy versus productivity when we use those 2 sets of data. Although the overall ranking between the 2 cycles is more or less the same, we notice some differences with respect to CPO27 nickel. And these differences can be attributed to differences in the adsorption isotherm predictions. If you look at the adsorption isotherms, the overall predictions may look reasonable, but the differences that we saw were CO2 capacity and in the low pressure region, and they have translated into the differences in performance. So this means that we need to validate the force fields that are used to predict adsorption isotherms by molecular simulations with reliable experimental data. We do acknowledge that the molecular simulation community is aware of this challenge and they are working towards it, but the main challenge comes from the experimental side. We have a large number of materials, and even for a single material, there is a large variation in the adsorption isotherm data. And we also need to remember that we need to obtain reliable nitrogen adsorption isotherm data for validating these 4 fields. And this is a significant challenge. With this, I would like to conclude my talk. I would like to thank the organizers of the conference for giving me an opportunity. Thank you all for your attention, and I will be happy to answer your questions. Thank you.